in today's lecture, I will basically finish this reliability aspect or reliability assessment of power distribution networks, and I will start with a problem, practical problem of a typical distribution network to assess the reliability of that particular network. Okay. So, look at this example. Okay. This example is very simple example. We have a substation at this point. This box is representing a substation or substation breaker, okay. And there is a primary feeder. There is a primary feeder, and this feeder is of 4 miles of length. So, length of the feeder is of 4 mile. Length of the feeder is 4 mile, out of which some part is overhead feeder. This 3 mile is some part is overhead feeder and some part is underground cable. So, overhead section is of 3 mile length and underground section is of 1 mile length. Okay. And it is also mentioned that there are 2 cable termination. There are 2 cable terminations after this particular feeder end, or that means the end of this particular feeder. So, let me go through this problem as a whole. So, the figure shows 4 mile long distribution feeder. Approximately 1 mile of the feeder has been built underground. Okay. Underground feeder is made of cable. Okay. You know that overhead feeder is made of overhead line conductors, and underground feeder is made of cable. Okay. So, approximately 1 mile of feeder has been built underground, while rest of the feeder is overhead. Okay. The underground feeder has 2 termination point, as I made. These are the cable termination, cable termination. Okay. Now, it is mentioned that 2 faults per circuit mile for overhead section and 1 fault per circuit mile for underground section of the feeder have been recorded in last 10 years. Okay. So, from this one need to extract this failure rate of this overhead section and underground section. Look at this sentence again. 2 faults per circuit mile for overhead section and 1 fault per circuit mile for the underground section of the feeder have been recorded in the last 10 years. Okay. The annual cable termination fault rate is given as 0.5% per cable termination. Furthermore, based on the past experience, it is known that the average repair times for the overhead section, underground section and each cable termination are 3, 30 and 3 hour respectively. Okay. So, these are the data given to you. What are the data given to you? Number 1 is failure rate of the overhead section of the feeder. Okay. What is that failure rate? It is 2 faults per circuit mile. Okay. Now, how we will get failure rate from this information, we will see. Okay. Similarly, there is 1 fault per circuit mile is recorded in last 10 years. So, failure rate is normally determined as a unit of number of faults per year. Okay. And here the failure rate is given as failure recording data is given as, or recorded failure data is given as 2 faults per circuit mile per unit length in fact for this overhead section and 1 fault per circuit mile or 1 fault per unit length for the underground cable. Okay. And also this based upon this experience, it is seen that the average repair time for this overhead section is 3 hour, underground section is 30 hour and each of the cable termination is of 3 hour. There is an important point that you can look at, that is the difference between failure rate and repair duration, that is lambda and r. We represent this failure rate by lambda, and repair duration, average repair duration you can say, that is r bar for overhead section and underground cable. What is the difference? First of all, this failure rate of overhead section is 2 faults per circuit mile, whereas that failure rate of this that underground cable is 1 fault per circuit mile. So, overhead section is having twice of the failure rate as the underground cable. Okay. And the repair duration of the overhead line is 3 hours and underground cable is 30 hours. So, it is because that because we have this overhead line conductors, its maintenance or repair time is less, but since it is a cable which is laid underground, the repair duration is higher. So, failure rate of this overhead line, although it is higher, but its repair duration is lower, and for this cable it is vice versa, that is failure rate is less, but repair duration is high. So, this is the one of the important observations that you can make, which is obvious. Now, using this information, you are supposed to determine the total annual failure rate or total annual fault rate of the feeder. Question number A. Question number B is average annual fault restoration time of the feeder, and question number C is unavailability of the feeder, and question number D is the availability of the feeder. This problem I took from Gonen book. Okay. And this, once you got this unavailability, availability as you have seen in my last lecture, it is just 1 minus that unavailability. So, fraction of time it is unavailable, which is equal to that 1 minus fraction of time it was available. Okay. So, these two can be easily found out, once we can find out at least one. Okay. Now, first of all we need to find out total annual fault rate of the feeder. So, to determine this, we have learned so many formula, and we know that how to determine that failure rate of a composite system. So, from that idea we have to determine that what would be the failure rate of the composite system. Now, here we have 3 different systems or 4 different systems which are connected in series. One is that overhead section. So, suppose overhead section I represent by OH, overhead section, this is one component. Another component is underground cable, that is UG section, underground section. Another component is cable termination 1, cable termination 1. Another component is cable termination 2, cable termination 2. Okay. So, these 4 components and they are in series. So, this is an example of, this is an example of 4 components which are repairable. So, 4 components which are repairable, are connected in series, Okay. So, this is an example of 4 components which are repairable and they are connected in series. So, in order to find out this composite or system failure rate, So, let me go back and check that what expression is applicable for that. So, if we go back and we see that when we have repairable components connected in series, the overall failure rate of the system is sum total of the individual failure rate of the components. Okay. So, this expression will be applicable to determine the overall failure rate of that feeder. Okay. So, here we have 4 system, that means n is equal to 4. Okay. So, that means we know that in order to find this first solution or answer of the first questions, we know that lambda c, that is failure rate of this overall system, or let us write it as failure rate of the feeder, is equal to lambda of the overhead section plus lambda of underground cable, underground section, plus lambda of first cable termination C T 1 and lambda of C T 2. Since both are identical, because as it is mentioned that this failure rates of both the cable are same. So, it is mentioned that the annual cable termination fault rate is given as 0.5% per cable termination. Okay. So, both the cable have same failure, both the cable terminations have same failure rate, okay, are of same failure rate. So, this lambda C T 1 and lambda C T 2 are equal. So, we can replace it as lambda feeder is equal to lambda of overhead section plus lambda of underground section plus lambda of one cable termination, and you multiply it 2, because both the cable terminations are identical. Okay. So, we write it in the next page that this here this O H represent this total annual fault rate of the overhead section, this lambda U G represents that total annual fault rate of the underground section, and lambda C T is representing total annual fault rate of the cable termination. Okay. Now, if we know this values of this lambda O H, lambda U G and lambda C T, we can find out that total annual failure rate or fault rate of the feeder. Okay. Now, it is mentioned that this overhead section is it is recorded that overhead section suffers from 2 faults per circuit mile in 10 years. Okay. So, we can find out overhead section failure rate as 2 faults per 10 years. So, in 1 year it is 2 divided by 10 faults. So, this is per circuit mile multiplied by its length. Its length is given as 3 mile, length of the overhead section is given as 3 mile. So, this multiplied by 3. Similarly, this lambda underground section is suffering from 1 fault per 10 years multiplied by its length, that is 1 mile, okay, because this fault is recorded per circuit mile, per circuit length. Similarly, this cable termination lambda C T we can find out as 0.5%. So, which is equal to 0.005. Okay. So, you put all these values over here, you will get this overall failure rate of the feeder is 0.71 faults per year. This is what the unit of the fault rate. Okay. So, first question is solved. So, we got this total annual fault rate of the feeder. Now, second is average annual fault restoration time of the feeder in hours. Okay. So, average annual restoration fault time means it is equal to R C bar. Okay. So, that represents this average annual fault restoration time or a fault repair time. Okay. Now, how to determine this R C bar for having this 4 subsystem or 4 components which are in series and which are repairable. So, let me go back again and check the formula. We already determined this R C bar is equal to this. So, which represents summation of this lambda I R I divided by summation of lambda I. Okay. So, where lambda I is basically the failure rate of the ith component or ith subsystem, R I represents that repair time or average repair time of the ith component. So, once we know all these things, we can find out this mean time to repair or mean restoration time. Okay. All right. So, in order to solve this question number 1, so let us find out this formula. This formula is directly applicable, that average annual fault restoration time is lambda I R I. Here we have 4 subsystems, but 2 systems are identical. So, they consider these 3 and we multiplied with factor 2 with this lambda C T. Okay. And this summation of this lambda I already we determined in the last slide, and we also know the individual failure rate of the system. So, which is determined as this number of faults divided by total time period it is recorded multiplied by its length. So, this L is basically LOH basically representing the length of the overhead section, length of overhead section. Similarly, LUG is basically representing length of underground section, and for this problem both are in mile, Okay. Now, and also this for cable termination, you know that it is lambda C T multiplied by R C T, and since there are 2 identical cable termination having identical failure rate and repair duration, so we can multiply it by factor 2. Okay. So, once you put all these values, in fact, this basically represents LOH multiplied by lambda OH is basically represent lambda I for overhead section. I write this overhead in short O by H. Okay. And similarly, this is basically representing lambda I for underground section. Okay. So, do not be confused with this. This is basically representing that failure rate of the overhead section and failure rate of the underground section. Since this number of falls recorded per unit length, so we multiply this length in order to find out the failure rate of the overhead section and failure rate of the underground section. Okay. So, you put this in this all these values over here, and we got this annual average restoration time or mean time to repair. This is basically nothing but mean time to repair for the feeder. Okay. So, that many hours. Okay. Now, we will determine that reliability for a parallel series combinations. Okay. So, as I said, in a practical power system, there may be several components, out of which some are connected in series and some are connected in parallel. So, this will make a series parallel combination. Okay. So, let us consider we have here n number of equipments which are connected in series, and this will constitute one unit. This is one unit, and there are so this is unit 1, and there are m number of such unit, So, we have n number of subsystems, they are connected in series and which constitute one unit of the system, and there are identical or maybe different, but there are m number of units, such unit are connected in parallel. Okay. So, for this we can find out this overall reliability of the system. So, assuming that individual here we have assumed that R is the reliability of the component. So, here the assumption is reliability of all components is identical and it is represented by R, capital R. Okay. So, once you consider that, it may so happen that these components reliability are different. If the components themselves are different, the reliability would be different. But if this assume that if we assume the reliability of individual components are identical, meaning that all components are identical. So, for a one particular unit which is a series combination of n number of such units connected in series. So, for this particular unit, the overall reliability will be r to the power n, because they are connected in series. So, we have such kind of we have m number of such kind of system where individual reliability of all this unit is identical, that is r to the power m. Now, as we know that when we have such kind of parallel combination, of m number of such units, and for parallel combination we know that unreliability function follow this product rule, that is 1 minus r to the power n will follow this product rule. So, we have m number of units. So, overall unreliability will be 1 minus r to the power n to the power m. Okay. So, they will follow this chain rule or product rule. Okay. So, this gives this unreliability of the overall system, and if you subtract with 1, then you will get the reliability of the composite system. Okay. Now, similarly, we may have m number of identical units connected in parallel, and we have n number of such units. So, this is unit 1, this is unit 2, and we have n number of such unit, this is unit n. Okay. This is unit n. Now, since they are in parallel, and here also we assume that all subsystems or all components are identical. So, here also our assumption is all components are identical. So, they have identical reliability. Okay. So, since we have m number of components are in parallel, and they will follow, since we know that for parallel components the unreliability function will follow this product rule. So, we know that 1 minus r, which would be the unreliability of individual component, they will follow this product rule. So, this to the power m will give you the unreliability of the individual system, that is q 1. So, this will be q 2 will be equal to 1 minus r to the power m, and so on. Now, as we know that for n number units connected in series, this reliability series component system or when we have a system having n number of components connected in series. So, their reliability will follow this product rule. So, if q 1 is that much, so r 1 will be equal to 1 minus r to the power m, and this will be same for n number of units. So, overall this reliability of the system will be R c will be equal to this to the power n, which is written over here. Okay. So, this is how we can determine the composite reliability for a system having n number of subsystem which are connected in series parallel combinations. Here we have m multiplied by n number of units, they are connected in series parallel fashion. Now, we have some example, these are easy example only. You need to determine that composite reliability or equivalent reliability of several subsystems connected in different fashion. For example, here 4 units are connected in series. So, composite reliability R equivalent will be equal to R to the power n, sorry here n is equal to 4. So, we can directly write as R to the power 4. Okay. Similarly, here this reliability level of this will be R to the power 4 and this will be also R to the power 4, okay. And they are in parallel. So, they are equivalent, they will follow this product rule of their unreliability function. So, unreliability function will be 1 minus R to the power 4 and that square will be total unreliability function of that system. So, reliability will be R equivalent will be equal to 1 minus this. Okay. So, this is the unreliability of this both this unit and so reliability will be that much. Similarly, all other, okay, and it is very simple to determine. Okay. So, first one is R to the power 4, second one is as I said 1 minus R to the power 4 square. So, this. So, third will be this example will be here the reliability is R square, here the reliability is R square and they will follow this product rule of their unreliability function, that is 1 minus R square. Okay. So, overall unreliability of this unit will be equal to 1 minus R square square. So, this will be total unreliability of this unit. Okay. Now, reliability will be 1 minus R square square. Now, we have such kind of 2 units are connected in series. So, overall R equivalent will be equal to 1 minus R square square that square. Okay. So, this is probably determined over here. So, this is 1 minus R square square. Okay. 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 All right. So, similarly, we determine this. Similarly, we can also determine the others. So, it is not difficult at all. So, if you try you can find out here the overall composite reliability will be equal to 1 minus R square. Okay. So, 1 minus R is basically unreliability of that unit and since we have 2 units in parallel. So, 1 minus R square will be the reliability of that unit. Okay. This has to be multiplied with the reliability with this unit. So, you can find out. So, as I said you can find out there should be a bracket here which is missing. Yeah. Okay. So, in that way you can find out and also you can find out for any combinations for example, here or whatever combinations. Okay. Now, we have another example. This example is says that we have 5 components A, B, C, D and E. They are connected in series combination like this A, B, C, D, E. Okay. And their individual reliability value is also given. R A is equal to given 0.8, R B is equal to given 0.95, R C is equal to given 0.99, R D is 0.9 and R E is 0.65. Then find out the first question is find out the equivalent system reliability. Find out the equivalent system reliability, which is not difficult as you know, since there are 5 components and all components are in series combination. So, R equivalent will be equal to R A multiplied by R B multiplied by R C multiplied by R D multiplied by R E. So, whatever you will get that will give this equivalent system reliability. Okay. Now, main interesting point is question number B, which says that if the equivalent system reliability is desired to be at least 0.8 or 80%, then design a system configuration to meet the system, meet this system requirement by using each of the 5 component at least one. Okay, by using each of the 5 components at least one. So, let me check that what is the equivalent system reliability value we get, that is by multiplying this 0.8, 0.95, 0.99, 0.9 and 0.65. We get this value as 0.44, okay, or 44.02%. If you multiply this individual reliability level of all these 5 units or 5 subsystems, then the composite reliability is coming out to be this. Okay. If you look at this value, then you see we have 2 components, one is having reliability is 0.65, another is reliability is 0.8. Because of these 2, the composite reliability become very less, okay, because see other 3 units having higher reliability value 0.95, 0.99, 0.9. So, their reliability values are pretty high, but since that unit consists of 5 subsystems connected in series and out of which one component is having very poor reliability level, that is 0.65, that composite reliability level is become very less as compared to these 3 units, okay, and this unit is also having moderate reliability level. So, what I mean to say is out of these 5 units we have at least 3 units B, C, D, they are having very good reliability level. But we have a unit, that is unit E, which is very poor reliability level, or we can write is poor reliability level, and we have another unit A, which is having good or moderate reliability level, but because they are connected in series. So, composite reliability is even less than the unit which is having the poor reliability level, which is having the least reliability level, that is 0.44, which I have in fact explained when I talked about the series units or a number of units connected in series. Now, because of that, this overall reliability level of the system becomes poor. So, what the second question is, we need to improve this reliability level of the composite system at least 80%, which is equal to this component A, at least using one component at least one time, because they have individual functionalities. Okay. Now, in practical power system, we may encounter this problem, and how do we solve this problem, or how do we come out from this problem? Suppose I have in fact, if you visit any power generation stations or power generation units, you will see there are many components, many auxiliary motors, many auxiliary switches, many auxiliary circuit breakers, and a number of devices which are required to produce the power. Okay. Now, all these components are very important. If one component is down, the overall unit would not generate any power. That is why, if you visit any power generating station, you will see for a certain task, if we need one component, okay, generally we have multiple backup components. So, that if that component fails, other backup component can be used to keep the work intact, okay, keep the main functionality of the system intact. Okay. So, here also one of the ways to improve this composite reliability of a system having n number of systems connected in series is to use multiple units for those components which are more prone of fault, which are having a less reliability level. Okay. And that is exactly done in order to achieve this composite reliability level. So, here as you see, we have out of these 5 components, as I categorized them, these 3 components B, C, D having a very good reliability level. So, their failure rate is very less. So, we do not bother about their failure. But since these 2 units R A and means A component A and component E, particularly this component E, this unit is this component is more prone to faults. So, what we need? We need to have some backup identical such units which should be connected in parallel. So, that the overall composite reliability becomes high. Okay. That is what exactly done here. So, what we did? We use B, C, D as there, and we use multiple components, multiple E components which are connected in parallel like this. So, that equivalent reliability level of this will improve. In fact, if we use 4 same units of this particular component E in parallel, then the composite reliability level is improved to be 0.985, which is pretty high. Okay. So, that if one unit fails, so other unit can be used in service. So, that the overall functionality of the system will be intact. Okay. Similarly, this since this reliability level of this component is very poor, so use 4 identical units. You can increase the number, and that will improve this equivalent reliability level of the system. Okay. So, here we have seen that by increasing it to 4 number, we got at least this desired reliability level. So, this is a kind of trial and error function. You keep increasing this particular component multiple times in parallel. So, that this you will get this composite reliability level to the desired value. And here we got that 4 E components or 4 E subsystems if you connect in series, and 4 A subsystems if you connect sorry not in series, in parallel, and 4 A subsystems if you connect in parallel, then their individual reliability levels will improve to 0.96 and 0.985, which makes the overall reliability of the composite system to the desired level, okay, to the desired level, which is 80%. Okay. So, how many number of this component A or component E we will be using, that will be trial and error. Okay. You keep on increasing this component E, so that you get a moderate value of, or not moderate, you get very high value of the individual reliability level. And similarly, you can keep on increasing, instead of these 2 components of A, if you add another component, of course, you will get that composite reliability level will be higher than 0.96, okay, and that will make this overall system reliability higher than 80%. Okay. So, how many component you will be using for A and how many components you will be using for E, that can be determined in a trial and error method. Okay. All right. So, the basic functionality should be understood that because of this very poor reliability level of this component E, we use several units are in parallel, and this at a time it may so happen one particular unit will be in operational and other units would be kept as a backup, So, that if there is any fault of that unit which is in operational, immediately we can run the other component. Okay. Or it may so happen that you can keep 2 units operational, both will perform 50% of their actual required work, and other 2 can be kept as a backup. Same thing you can see if you visit any power station, particularly there are some motors where which have some specific work, and we need only 2 motors to have a full generation, but we keep the total number at least 4. So, that if any one trips, another immediately come, another will be brought to the service immediately. Okay. Now, we have another example. This example is of a 3-phase transformer. This 3-phase transformer bank consists of 3 single phase transformers identified as A, B and C. Okay. And transformer, we often know that one 3-phase transformer is made of 3 single phase transformer bank. Same thing is the problem is of similar concept. Okay. So, transformer A is an old unit and therefore, reliability is 0.9. Okay. Transformer B has been operational for last 20 years and therefore, its reliability is 0.95, and transformer C is a brand new and its reliability is 0.99. Now, you can see this aging effect is visible here. With time, this reliability level of individual component will reduce, which I discussed at the very beginning of this mathematical description of failure function and the reliability function. Okay. So, based on this information, determine the probability of having no failing transformer at any given time, that is basically the reliability level of the overall system having 3 transformers. Second is, if one out of these 3 transformer fails at any given of time, what would be the probabilities of that unit being the transformer A, transformer B and transformer C. That means, what is the probability of the failure of individual transformers A, B and C. Okay. And if there is a simultaneous failure of 2 transformers, what would be the probability of the transformers A and B to simultaneously fail, and B and C to simultaneously fail, and C and A to simultaneously fail, and what would be the probability of having all these 3 transformer out of service at a given time. Okay. So, we know that individual reliability level transformer A R A is equal to 0.9, transformer B R B is equal to 0.95 and transformer C R C is equal to 0.99. Okay. This is something which is given to us. Okay. Now, what would be that probability of having all the transformer operational without any fail? So, that will be the reliability level of the system. So, you multiply all these 3, you get, that is 0.84645, which is similar to 84.645 percentage. Okay. So, that much time, that percentage of time, there will be no faults at all. Okay. Our system will be operational in healthy condition. Now, what would be the failure faults if we have one fault of individual transformer at a time. So, if we have one fault at a time. So, this event is translated as A prime. So, probability of A is basically representing this reliability of the system, that is probability for transformer A not to fail. Okay. Now, what would be that probability of the transformer A or failure probability of the transformer, which is 1 minus this P A, which is equal to P A prime, which is 0.1, and for that particular event the probability is this. Similarly, this this basically represents that A and C are healthy and B is faulty. This particular event is representing B and C healthy, A is faulty, and this particular event representing A and B healthy, C is faulty, and their individual probability values you can determine. Okay. So, this is an example of one transformer fault at a time. So, this is a scenario of one transformer faults fault at any time. Okay. So, individual probability you can determine. Similarly, if we have simultaneous failures of the transformer. So, here this is the example of simultaneous failure of two transformers. Okay. So, we have two transformers fail at a time, that is A and B, C is healthy. Okay. Here we have two transformer B and C are having this failure, where A is healthy, and this is the case where this A and C will encounter faults simultaneously when B is healthy. Okay. So, individual probability you can find out. All right. Now, what would be the probability of having all the three transformers out of service at any given time, which is equal to this probability or this, as you know, this intersection of these three events, where A prime, B prime and C bar, or A bar, B bar and C bar, they represent the failure event of individual transformer. And when this happens simultaneously, so this probability is equal to this. Okay. So, here since we have 3 units, there are 4 different scenarios. On scenario 1 is all the units will be in healthy. Scenario 2 is there would be one fault, one transformer failure at any time. Scenario 3 is there would be 2 simultaneous failures or two failures, or that means 2 units of transformer will fail simultaneously, and the fourth scenario is all this transformer will fail simultaneously. Okay. And if you add up all this probability value, you will get this total value will be equal to 1, which is the sum total of all these 4 events. So, 0 stands for no failure, 3 stands for all failure, 1 stands for one transformer fault, So, this happens for 3 times, that means when A failed, when B failed and when C failed, and this is another scenario where 2 transformers fault, 2 transformers faults will take place simultaneously, and there are 3 possible cases. One is when A and B, here this would be B prime, A and B will simultaneously fail, when B and C are simultaneously fail, and when A and C are simultaneously fail. Okay. So, if you add all this, you will get the overall event probability is equal to 1. Now, at the end of this particular lecture, I will talk about something called stochastic modeling of this reliability, and I will discuss this Markov process, okay, or Markovian chain. Okay. So, in reliability studies, the variable t represents time that we know, and x t represents state of the system, okay, at time t. Now, what do you mean by state of the system? So, this state at any given time is actually represent the outcome of the system at that time. Alternatively, you can consider that a state is defined as those property of a system which adequately represent the system behavior. Okay. So, in Markov process, which is a stochastic process, it says that occurrence of any future state depends on the immediately preceding state and only on it. That means, for any particular state, occurrence or probability of the occurrence of that state is only depends upon its previous state, not all the preceding states. Okay. And that is why this Markov process called by lack of memory, it is a kind of memory less stochastic process. Okay. And we have some mathematical description to describe this. So, this P x T n basically representing this probability of this state x at time t n, which is also represented by small x n, such that x t 1 is represented x 1. That means, this state x at this time t 1 is represented by small x 1, x t 2 represented by small x 2, and so on. Okay. So, this is basically similar to this probability of x t n is equal to x n and its preceding state, that is at t minus n is equal to x minus n. Okay. So, this is called Markovian property. Now, we have a concept of transition probability from one state to another state. For example, this basically gives you the transition probability of state x n from this state x minus n. Okay. So, for any state of n time points where t is gradually increasing, t 1 less than t 2 less than to t n, t is gradually increasing, and there are real number x 1, x 2 to x n. The probability of or rather transition probability is the conditional probability of the system for being at x n at t n, given that it was at x minus n at t minus 1. Okay. So, it means that it gives a probability that any system will be at x n at t is equal to t n, provided that it was at its state was at x n minus 1, that is this at t n minus 1. Okay. So, this basically gives this one step transition probability. Okay. So, we can also find out k step transition probability, that means any system state will be at x n plus k at t n plus k, provided that it was at x n at t is equal to t n. Okay. And also we have a concept of Markov chain. Markov is a Russian mathematician. So, he defined this concept called as Markov chain, which is defined as a sequence of discrete value random variable, which is represented by x t n, where t n is the discrete value or continuous. Therefore, one can also define the Markov chain as Markov process with discrete state space, where this p I j is equal to this probability for having the system at j at t is equal to t n, provided that it was at I state I at t is equal to t minus n. Okay. So, at one step transition probability of going from state I to state at state I at t minus 1 to state j at t n, and assume that these probabilities do not change over time. Okay. So, this probabilities is constant over time, and that is why it is also called as stationarity property. Okay. Now, in Markov chain we determine a probability matrix. It is represented by a probability matrix, which is called one step transition matrix, okay, where all these individual elements are representing this transition probability. That means, P 00 represent the transition probability of any particular system to stay at 0 state if it was at 0 state before. Okay. Similarly, P 01 represent the transition probability to state 1 provided that it was at state 0 before, and so on. Okay. And if sum of this one particular the P I j over j is equal to 1 to n is basically equal to 1 for all I. Okay. Now, this is called a transition diagram, where we have three different states of a system, and these arrows basically represent this transition probability. So, P 11 represents the transition probability to stay at state 1 provided that it was at state 1 before. Okay. And P 12 is basically transition probability to go at state 2 provided that it was at state A before. Similarly, P 21 is transition probability to go to state 1 provided that it was at state 2 before, and so on. Okay. So, I have a small example which would be useful to understand the concept, that a distribution utility having a 2% of transformer that are presently down, and therefore, being repaired now will be down also, and therefore, we will need repair next time. So, there are 2% transformer which are presently down, and after repairing there is a probability that they will be down. Okay. And record also shows that the 5% of those transformer that are currently up and therefore, in service now will be down, and therefore, we will need repair next time. Okay. Assuming that the process is discrete Markovian and has a stationary transition probability. Stationary transition probability means these transition probabilities are independent, are constant, does not vary with time. So, determine the transition diagram. Okay. So, here we have two states, one is state up, another is state down. So, we have two states, one is up, another is down. So, it is a two state model. So, we represent that individual probability that those transformer which are down presently, they will be down in after repair also, that probability is 0.2. Now, it is also given that some transformer which are down will be up, that probability is equal to 0.5, 0.05, that is 5% transformer which are presently up and therefore, in service will be down. Okay. So, they are now up, in future they will be down. Okay. And so, who are up will be also up, that will be 1 minus 0.5, that is 0.95, and presently who are down, who will be up, who will be equal to 1 minus 0.2, that is equal to 0.98. Okay. So, these are the elements a transition matrix, and this transition matrix will look like this, where this represent this transition probability to stay at down previous for those whoever was down before, but this is the probability to switch from down to up. Okay. Similarly, this is the probability who are in up, who will stay will be down, and these are the probability who are up, which will stay at up. Okay. Now, this is basically this transition diagram. Here you can see the state 1 is basically represented as down, state 2 is basically represented as up. So, those who are down will stay at down, that transition probability is 2%. So, next 98% will go to up. Okay. And those transformer who are up, they will stay down, that probability will be 5%, and rest 95% will stay up. Okay. So, this is how we represent this fault events using this Markovian process. And all these materials I took from this book, Gonen book, and this is the main reference for this particular module. And this is of course, this part 1, this module 3, and another module I will discuss next lecture, that will be part 2 of that module, where we will talk about some power quality problems, okay, for typical distribution system. Okay. So, thank you very much for attending this lecture.